Network science. From Wikipedia, the free encyclopedia. For other users, see network disambiguation. Network science is an academic field which studies complex networks such as telecommunication networks, computer networks, biological networks, cognitive networks, and semantic networks, and social networks. Considering distinct elements or actors represented by nodes or vertices, and the connections between the elements or actors and as links or edges. The field draws on theories and methods including graph theory from mathematics, statistical mechanics from physics, data mining, and information visualization from computer science, inferential modeling from statistics, and social structure from sociology. The United States National Research Council defines network science as the study of network representations of physical, biological, and social phenomena leading to predictive models of these phenomena. Background and history. The study of networks has emerged in diverse disciplines as a means of analyzing complex relational data. The earliest known paper in this field is the famous Seven Bridges of Königsberg, written by Coates in 1736. His mathematical description of vertices and edges was the foundation of graph theory, a branch of mathematics that studies the properties of pairwise relations in a network structure. The field of graph theory continued to develop and found applications in chemistry. In 1878, Coates, a Hungarian mathematician and professor, who wrote this book in graph theory entitled Theory of Finite and Infinite Graphs in 1936. In the 1930s, Coates, a physiologist in the Gestalt tradition, arrived in the United States. He developed the sociogram and presented it to the public in April 1933 at the Convention of Medical Scholars. Marino claimed that before the advent of sociometry, no one knew what the interpersonal structure of a group precisely looked like. Coates, 1953. The sociogram was a representation of the social structure of a group of elementary school students. They were friends, and the girls were friends, and with the exception of one slack single girl. The film was not pre-propagated. This network representation of social structure was found so intriguing that it was printed in the New York Times, April 3, 1933, page 17. The sociogram has found many applications and has grown into the field of social network analysis. Probabilistic theory in network science developed as an offshoot of graph theory, with Coates and Coates' 8 famous papers on random graphs. For social networks, the exponential random graph model, or P*, is a notational framework used to represent the probability space of a tie occurring in a social network. An alternate approach to network probability structures is a network probability matrix, which models the probability of edges occurring in a network based on the historic presence or absence of the edge in a sample of networks. In 1998, Coates and Coates introduced the idea of a meta-network with the PCANS model. They suggest that all now, okay, we jump back to the, what is this, man? This may indicate that for many real-time applications, the service quality of existing on-chip interconnect infrastructure is sufficient, and dedicated hardware logic would be necessary to achieve microsecond precision, a degree that is rarely needed in practice. For end users, sound and video data need only 10 to milliseconds latency guarantee. Another motivation for NOC, the level of quality of service QoC, is to support multiple concurrent users sharing resources of a single chip multiprocessor in the public cloud computing infrastructure. In such instances, hardware quality of service logic enables a service provider to make contractual guarantees on the level of service that the user receives, a feature that may be deemed desirable by some corporate or government clients. Many challenging research problems remain to be solved at all levels, from the physical link level to the network level, and all the way up to the system architecture and application software. The first dedicated research symposium on networks on chip was held at Princeton University in May 2007. The second IEEE International Symposium on Networks on Chip was held in April 2008 at Newcastle University. Research has been conducted on integrated optical waveguides and devices comprising an optical network on chip, ONOC. The possible way to increase the performance of NOC is use wireless communication channels between chiplets. named Wireless Network on Chip, WINOC. Side benefits: in a multi-core system connected by NOC, coherency, messages, and cache miss requests have to pass switches. Accordingly, switches can be augmented with simple tracking and forwarding elements to detect which cache blocks will be requested in the future by which cores. Then, the forwarding elements multicast the requested block to all the cores that may request the block in the future. This mechanism reduces cache miss rate. Benchmarks: NOC development and studies require comparing different proposals and options. NOC traffic patterns are under development to help such evaluations. Existing NOC benchmarks include NOC bench and MCSL NOC traffic patterns. Interconnect processing unit. An interconnect processing unit, IPU, is an on-chip communication network with hardware and software components which jointly implement key functions of different system-on-chip programming models through a set of communication and synchronization primitives, and provide low-level platform services to enable advanced features in modern heterogeneous applications on a single die. See also Arteris, Electronic Design Automation, EDA, Integrated Circuit Design, CUDA, Globally Asynchronous, Locally Asynchronous Network Architecture. Notes: this article uses the convention that NOC is pronounced NOC, therefore it uses the conventional A for the indefinite article corresponding to NOC, a NOC. Other sources may pronounce it as NOC and therefore use an NOC. Then you got the reference, a whole bunch of references. And the suppliers of manufacture of motor chips. Whoa, a lot of motor chips. The whole page is depleted of motor chips. Let's go with CPU. A binary decoder. A binary decoder from Wikipedia, Free Encyclopedia. This article needs additional citations for verification. Please help improve this article by adding citations to reliable sources. Unsourced material may be challenged and removed. Find sources: binary decoder, news, newspapers, books, Scholar, JSTOR, May 2009. Learn how and when to remove this type of message. In digital electronics, a binary decoder is a combinational logic circuit that converts binary information from the encoded inputs to a maximum of 2n unique outputs. They are used in a wide variety of applications, including instruction decoding, data multiplexing, and data demultiplexing. 7-segment displays and as address decoders for memory and port maps input-output. There are several types of binary decoders, but in all cases, a decoder is an electronic circuit with multiple input and multiple output signals, which converts every unique combination of input states to a specific combination of output states. In addition to integer data inputs, some decoders also have one or more enabled inputs. When the enabled input is disabled, all decoder outputs are forced into their inactive states. Depending on its function, a binary decoder will convert binary information from input signals to as many as 2n unique output signals. Some decoders have less than 2n output lines. In such cases, at least one output pattern may be repeated for different input values. A binary decoder is usually implemented as either a standalone integrated circuit, IC, or as part of more complex IC. In the latter case, the decoder may be synthesized by means of hardware description language, such as VHDL or Verilog. Widely used decoders are often available in the form of standardized ICs. Types of decoders: one of n decoder. One of n binary decoder has n output bits. This type of decoder asserts exactly one of its n output bits, or none of them. For every integer input value, the addressed bit number of the activated outputs is specified by the integer input value. For example, output bit number 0 is selected when the integer value is 0. Value 0 is applied to the inputs. Examples of this type of decoder include a 3 to 8 line decoder activates one of 8 output bits for each input value from 0 to 7. The range of integer values can be expressed in 3 bits. Similarly, a 4 to 16 line decoder activates one of 16 outputs for each 4-bit input in the integer range 0 to 0,15. A BCD to decimal decoder that has 10 output bits. It accepts an input value consisting of a binary coded decimal integer value and activates one specific unique output. For every input value in the range 0,9, all outputs are held inactive when a non-decimal value is applied to the inputs. A demultiplexer is a one of n binary decoder that is used to route a data bit to one of its n outputs, while all other outputs remain inactive. Code translators differ from one of n decoders that multiple output bits may be active at the same time. An example of this is a 7-segment decoder which converts an integer into the combination of segment control. Signals needed to display the integer's value on a 7-segment display digit. One variant of 7-segment decoder is the BCD to 7-segment decoder, which translates a binary coded decimal value into the corresponding segment control signals for input integer values 0 to 9. This decoder function is available in standard ICs such as the CMOS 4411 binary to unary decoder. A binary to unary decoder converts each binary value to its associated unary representation. Unlike the 1n 1-hot decoder, multiple output bits can be asserted for each input value. These decoders can be used in DACs, DACs, where each bit is equally weighted, and circuits that require binary mask or window. See also multiplexer, 1-hot. The format of the 1 of n decoder's output, or the unencoded output of a ring counter, priority encoder, sum address decoder, references, mail to the references, slide back, and see CPU multiplier. In computing, the clock multiplier or CPU multiplier or bus core ratio sets the ratio of an internal CPU clock rate to the external supplied clock. This may be implemented with phase-locked loop (PLL) frequency multiplier circuitry. A CPU with a 10 times multiplier will thus see 10 internal cycles for every external clock cycle. For example, a system with an external clock of 100 MHz and a 36 times clock multiplier will have an internal CPU clock of 33.6 GHz. The external address and data buses of a CPU, often collectively termed frontside bus, FSB in PC context, also use the external clock as a fundamental timing base. However, they could also employ a small multiple of this base frequency, typically 2 or 4, to transfer data faster. The internal frequency of microprocessors is usually based on FSB frequency. To calculate internal frequency, the CPU multiplies bus frequency by a number called the clock multiplier. For calculation, the CPU uses actual bus frequency and not effective bus frequency to determine the actual bus frequency for processors that use dual data rate DDR buses, AMD, Athlon, and Duron, and quad data rate buses. All Intel microprocessors starting from Pentium 4. The effective bus speed should be divided by 2 for AMD or 4 for Intel. Clock multipliers on many modern processors are fixed. It is usually not possible to change them. Some versions of microprocessors have clock multipliers unlocked. That is, they can be overclocked by increasing the clock multiplier setting in the motherboard's BIOS setup program. Some CPU engineering samples may also have the clock multiplier unlocked. Many Intel qualification samples have maximum clock multiplier locked. These CPUs may be underclocked, run at low frequency, but they cannot be overclocked by increasing clock multiplier higher than intended by CPU design. While these qualification samples in the majority of production microprocessors cannot be overclocked by increasing their clock multiplier, they still can be overclocked by using a different technique by increasing FSB frequency. Basic system structure. As of 2009, computers have several interconnected devices, CPU, RAM, peripherals, etc. See diagram. They typically run at different speeds. Thus, they use internal buffers and caches when communicating with each other via the shared buses in the system. In PCs, the CPU's external address and data buses connect the CPU to the rest of the system via the NOR bridge. Nearly every desktop CPU produced since the introduction of the 486DX2 in 1992 has employed the clock multiplier to run its internal logic at a higher frequency than its external bus, but still remain synchronous with it. This improves the CPU performance by relying on internal cache memories or wide buses, often also capable of more than one transfer per clock cycle, to make up for the frequency difference. Variants, some CPUs such as Athlon 64 and Opteron handle main memory using a separate and dedicated low-level memory bus. These processors communicate with other devices in the system, including other CPUs, using one or more slightly higher level hypertransport links, like the data and address buses in other designs. These links employ the external clock for data transfer timing, typically 800 MHz or 1 GHz as of 2007. BIOS settings. Some systems allow owners to change the clock multiplier in the BIOS menu. Increasing the clock multiplier will increase the CPU clock speed without affecting the clock speed of other components. Increasing the external clock and bus speed will affect the CPU as well as RAM and other components. Now, these adjustments provide the two common methods of overclocking and underclocking in a computer, perhaps combined with some adjustments of CPU or memory voltages. Changing oscillators crystals occurs only rarely. Note that careless overclocking can cause damage to the CPU or other components due to overheating or even voltage breakdown. Newer CPUs often have a locked clock multiplier, meaning that the bus speed or the clock multiplier cannot be changed in the BIOS unless the user hacks the CPU to unlock the multiplier. High-end CPUs, however, normally have an unlocked clock multiplier. Clock doubling. The phrase clock doubling implies a clock multiplier of 2. Examples of clock doubled CPUs include the Intel 80486DX2, which ran at 50 or 66 MHz on a 25 or 33 MHz bus. The Waytech Spark Power, Macro P, is a clock doubled 80 MHz version of the Spark processor that one could drop into the otherwise 40 MHz Spark Station 2. In both these cases, the overall speed of the systems increased by about 75%. By the late 1990s, almost all high-performance processors, excluding typical embedded systems, run at higher speeds than the external buses. So the term clock doubling has lost much of its impact. For CPU-bound applications, clock doubling will theoretically improve the overall performance of the machine substantially. Provide the fetching of data from memory does not provide a bottleneck. In more modern processors, where the multiplier greatly exceeds 2, the bandwidth and latency of specific memory ICs or the bus or memory controller typically become a limiting factor. See also memory divider. Memory divider. From Wikipedia, the Free Encyclopedia. This article needs additional citations for verification. Please help improve this article by adding citations to reliable sources. Unsourced material may be challenged and removed. Find sources, memory divider, newspapers, books, Scholar, JSTOR, October 2008. Learn how and when to remove this template message. A memory divider is a ratio which is used to determine the operating clock frequency a computer memory in accordance with frontside bus FSB frequency. If the memory system is dependent on FSB clock speed along with memory latency timings, memory dividers are extensively used in overclocking memory subsystems to find stable working memory states at higher FSB frequencies. The ratio between DRAM and FSB is commonly referred to as DRAM:FSB ratio. Memory dividers are only applicable to those chipsets in which memory speed is dependent on FSB speeds. Certain chipsets like NVIDIA S680i have separated memory and FSB lanes, due to which memory clock and FSB clock are asynchronous, and memory dividers are not used there. Setting memory speeds and overclocking memory systems in such chipsets are different issues which do not use memory dividers. This article is only applicable to those chipsets in which the memory clock is dependent on FSB clock. Overview. Memory dividers allow system memory to run slower than or faster than the actual FSB frontside bus speed. Ideally, frontside bus and system memory should run at the same clock speed because FSB connects system memory to the CPU, but it is sometimes desired to run the FSB and system memory at different clock speeds. It is possible to run FSB and memory clock at different clock speeds within certain limits of the motherboard and corresponding chipset. So settings termed as memory divider or FSB DRAM settings are available and are expressed in a ratio which control the difference in memory clock rate and FSB speed. Entry-level motherboards usually do not provide memory dividers to be changed, and the memory dividers are managed by memory controller. If a chipset supports memory dividers, high-end motherboards meant for overclocking provide facilities to change memory dividers. If a chipset supports memory dividers, however, in certain chipsets, memory dividers are not used because in those systems, memory speed is independent of FSB speed. Description and application. Usually, memory divider. We are going to grab some lemonade. I'm reaching the fridge. I'm reaching for fridge. I'm opening the fridge. It's open. I take my Coca-Cola, close the fridge, and sit back in my seat. By default FSB speed and memory are usually set to 1:1 ratio, meaning that increasing FSB speed by overclocking increases memory speed by the same amount. Normally, system memory is not built for overclocking and thus may not be able to take the level of overclocking that the processor or motherboard can achieve. The memory divider allows users to mitigate this problem by reducing the speed increase of the memory relative to that of the FSB and the processor. Example. We've reached an example. Example. Suppose the computer system has DDR memory, a memory divider of 1:1 and FSB operating at 200 MHz and CPU multiplier of 10x, then the base memory clock will operate at memory divider X FSB is 1 times 200 is 200 MHz, and the effective memory clock would be 400 MHz since it is a DDR system. DDR stands for double data rate. The effective memory clock speed is double the actual clock speed. The CPU will operate at 10 times 200 MHz. It's 2 GHz. Using high input-output bus frequency of 200 MHz, various types of DRAM will operate as DDR SDRAM at 400 MHz, DDR400 or PC 3200. DDR2 SDRAM at 800 MHz, DDR2 800 or PC 26400. DDR3 SDRAM at 1600 MHz, DDR3 1600 or PC3 12800. Now suppose that we overclock FSB to 250 MHz, so that CPU operates at 10 times 250 MHz is 2.5 GHz and memory clock operates at 250 MHz. Memory divided times FSB. Since DDR400 RAM is used as effective memory clock, actual memory frequency will be 500 MHz. A normal DDR400 SD RAM will fail to work at 500 MHz since it is designed to work at 400 MHz, and the system will become unstable. But the modern CPU having overclocking potential can work at 2.5 GHz. Even if it is designed to work at 2 GHz flawlessly, without giving any problem of stability, to keep running overclocked CPU at 2.5 GHz or even at higher speeds by increasing the FSB, we need to slow down memory clock so as to achieve a stable system. For this, we decrease our DRAM FSB ratio to say 4:5. The resulting memory clock speed is 4 to the 4 divided by 5 times 250 megahertz, 200 megahertz, resulting effective clock speed of 400 megahertz on DDR 400. So we are able to operate upon an unstable overclocked CPU at 2.5 gigahertz from 2 gigahertz without increasing effective memory clock. See also CPU multiplier. CPU multiplier from Wikipedia, the free encyclopedia. In computing, the clock multiplier or CPU multiplier or bus core ratio starts the ratio of an internal CPU clock rate to the external supplied clock. This may be implemented with phase locked loop (PLL) frequency multiplier circuitry. A CPU with a 10 times multiplier with a class C 10 internal cycles for every internal clock cycle. For example, a system with an external clock of 100 MHz and a 36 times clock multiplier will have an internal CPU clock of 36 GHz. The external address and data buses of the CPU, often collectively termed frontside bus, FSB, and PC context, also use the external clock as a fundamental timing base. However, they could also employ a small multiple of this base frequency, typically 204, to transfer the data phase faster. The internal frequency of microprocessors is usually based on FSB frequency. To calculate internal frequency, the CPU multiplies bus frequency by a number called the clock multiplier. For calculation, the CPU uses actual bus frequency and not effective bus frequency. To determine the actual bus frequency for processors that use dual data rate DDR buses, AMD Athlon and Duron, and quad data rate buses, all Intel microprocessors starting from Pentium 4, the effective bus speed should be divided by 2 for AMD or 4 for Intel. Clock multipliers on many modern processors are fixed. It is usually not possible to change them. Some versions of processors have clock multipliers unlocked, that is, they can be overclocked by increasing the clock multiplier setting in the motherboard's bus setter program. Some CPU engineering samples may also have the clock multiplier unlocked. Many Intel qualification samples have maximum clock multiplier locked. These CPUs may be underclocked, run at lower frequency, but they cannot be overclocked by increasing clock multiplier higher than the intended by CPU design. While these qualification samples in the majority of production microprocessors cannot be overclocked by increasing the clock multiplier, they still can be overclocked by using a different technique by increasing FSB frequency. Basic system structure. As of 2009, computers have several interconnected devices, CPU, RAM, peripherals, etc. I see diagram, that typically run at different speeds. Thus they use internal buffers and caches when communicating with each other via the shared buses in the system. In PCs, the CPU, external address and data buses connect the CPU to the rest of the system via the node bridge. Nearly every desktop CPU produced since the introduction of the 486DX2 in 1992 has employed the clock multiplier to its internal logic at the high frequency that is external bus but still remains synchronous with it. This improves the CPU performance by relying on internal cache memories, wide buses, often also capable of more than one transfer per clock cycle. To make up for the frequency difference, variants, some CPUs, such as Athlon 64 Opteron, handle main memory using a separate and dedicated low-level memory bus. These processors communicate with other devices in the system, including other CPUs, using one or more slightly higher level hypertransport links like the data and address buses and other designs. These links employ the external clock for data transfer to timing, unblemished on it. Typically 800 MHz or 1 GHz as of 2007. BIOS settings. Some systems allow owners to change the clock multiplier in the BIOS menu. Increasing the clock multiplier will increase the CPU clock speed without affecting the clock speed of other components. Increasing the external clock and bus speed will affect the CPU as well as RAM and other components. Now, We cannot go further now anymore because we have reached 30 minutes. We're going to stop right here.